All right, so let's sort of recap where we left off last time. I figure, like last time, we'll cover some stuff for a little bit, take a break, cover some stuff a little bit more, and then call it to sort of keep the same format. So last time what we were talking about was the concept of section properties because, or at least that's where we ended off. The idea is that we need to at least have some formative discussion of this stuff right now, because later on, when I start referring to things like DC loads and DW loads and looking at things like live load plus impact and structural analysis considerations and all this stuff, these are the types of calculations that we need to make sure that we're all clear with now, because we're going to refer to a lot of this stuff later on. So it makes sense to sort of take some time and talk about this now. So we went through some of this. I'm going to go through this real quick since we did this last time. But when I say section properties, I mean things like areas, moment of inertia, section moduli, things like that. All right. The reason why all this stuff was important was because of loading sequence. Remember, we said, if you've got a typical steel bridge, you look at the steel girder by itself. That steel girder by itself has to be able to resist all of the loads of the self-weight of the steel, all the cross frames, the studs, the formwork, the wet concrete, all of that. But once the concrete cures, the bridge as a whole resists the vehicular load. Not just the steel beam, it's the steel and the concrete acting together. So we have to be able to consider that load sequence. All right? Then we spent a little bit of time talking about the terminology, things like making sure that we all understood what the top flange, bottom flange, and web was, what I meant by the haunch, what I meant by an integral or a sacrificial wearing surface and things. We went and spent some time defining specifically what the haunch is, why it exists, typically because of formwork and setting deck elevations and what have you. Looked at the integral wearing surface. We assumed there's a small layer of concrete on the top of that deck that's inefficient, and that's because over time it wears away. That's a big reason for it. But just general wear and tear, we assume some of that goes away. We also talked about the effective flange width, the idea that a portion of that deck is going to be efficient for that girder, not all of it. So if I'm isolating a given girder, what portion of that deck am I going to consider? And we went through and talked about the behavior, and ultimately it was just the tributary width, and that was a piece of the spec. You all now have a couple sets of the spec. You don't have Section 4 yet, or at least the pieces of Section 4 that you need. You will later when we start really digging into Section 4. For now, just sort of take my word. I promise this comes from the AASHTO spec. All right. So ultimately, for effective flange width, it's just the tributary width, halfway between adjacent girders. And we went through and did that. Let's see, what else? Because of the fact that it's tributary width that we're going to be considering, and just the concept in general, we can have different effective flange widths for the girders on the outside versus the girders on the inside. So exterior girders can have different section properties than interior girders. Typically, exterior girders have lower section properties. They're typically weaker because the effective flange width is smaller out here than it is in the middle. Most of the times when you design a composite steel plate girder bridge like this, it's the exterior girder that governs the design. You can go through and do all your math, and you'll find that the interior girder is fine as long as you use the same shape. All right. There's also other reasons why the exterior girders tend to control, and that's also from the load side. Particularly when you look at the live load, these beams tend to see a lot more live load than these, and we'll be able to numerically illustrate that later, but that's a little bit down the road. All right. So far, so good? And last week, we looked at things like, going back to mechanics, we can't deal with two materials using just basic beam bending, so we have to convert one of those into the other. For what we do, we take the concrete, we turn it into an effective lump of steel by dividing by the modular ratio, which is just Young's modulus for steel divided by Young's modulus for concrete. Young's modulus for steel is a constant value of 29,000. That again comes from the spec, and it's also just basic steel behavior. Concrete, it's a little more convoluted. You have to compute it. There's a shortcut that you can use, however, for normal weight concrete, just 1820 times the square root of FC prime. Let's see. So far, so good? All right. Last thing, we needed to look at the difference between short-term, long-term. I keep saying last, but then there's things I forgot. All right. We looked at the difference between short-term and long-term composite sections, and that was, we were starting to get a little bit into the minutia. Basically, things like, once the, once we're, let's go back to the evolution of load on a bridge. So we set the beams down, set the cross frames, form work, pour the deck. All that load is resisted by the steel girder by itself. When I run a truck on that bridge, when I run the truck, it doesn't act on the bridge for a very long time. The truck's on and it's off, on and it's off, and that's it. So we apply those loads to what we call the short-term composite section because live loads are only on the bridge for a short term, a short period of time. And we determine that section by dividing the effective deck width by N, by that modular ratio. But if we look at other dead loads that are there the entire time, things like the concrete jersey barrier, things like any utilities or any signs on the structure, well, those things are there, and they're there for the duration. They're always on the bridge, okay? So instead of dividing those by N to generate a short-term composite section, we divide by 3N to generate a long-term composite section. Those are the loads that are applied on the long term. So graphically, this is what we got going on. Anybody got any questions about that? All right. Now, we sort of handled most of this last time. What we didn't handle was the negative bending region, specifically these regions over the pier. Because over the pier, the bridge is bending kind of like this, so the concrete is in tension, okay? And concrete is a material that really doesn't like to be in tension. So because of that, we really can't count, or in most cases, I'll say, we can't count on that concrete deck being effective, but what we can count on is that reinforcement. So we have a fourth section that we consider for negative bending, and that's the steel plus longitudinal reinforcement. We got a nice little shortcut that the code provides. We don't have to take the bridge plans and sit there and count up each little piece of rebar in the effective flange width. All we have to do is take the total area of deck that's in that effective flange width, take 1% of it, and say that's our rebar. Split it up into thirds. We take 2/3, place it on the top, 1/3, place it on the bottom, and that's it. Now, top and bottom, that's a little vague. So what do I mean by top and bottom? I'm talking about cover requirements. So on the top, let's say we're talking about a bridge here in West Virginia. If you've been here during the winter, you know that we like to put a lot of salt on the roads. So any surface that is subjected to exposure to de-icing salts, we got to have a cover of at least 2.5 inches. And these cover requirements would vary depending on where we're at. I mean, what if we were designing a bridge or we're looking at a column or something out in Miami? That's obviously going to be exposed to something like salt water, so maybe we need more stringent cover requirements. For the bottom bars, anything up to a number 11, 1 inch. Okay? Sound good? All right. So for negative bending, we have an additional section we got to consider, and that's this one, larger amount of rebar going on the top. All right, and we started to look at this with the following example. We took this example, started to break it up into its individual components, and getting back to all that stuff y'all learned in statics way back when, and strength of materials, moments of inertia, section properties and things like that. All right, so we looked at this structure, and we went through and discussed how to compute non-composite section properties and then composite ones. And what we found was it really doesn't matter, like once you've gotten the composite section properties down pat, they're all the same, really. I mean, what's the difference between short term and long term? It's just a different N value. Instead of N, it's 3N. What's the difference between interior girder properties and exterior girder properties? It's just a different flange width. In the end, it's all the same, okay? What's the difference between the positive bending region and the negative bending region? Well, the only difference is that the girder's a different size, right? In the end, the calculation's all the same. So last time all we did was this. We did the calculation for, just a single steel beam and then a steel beam plus concrete. But in the end, it's all pretty interchangeable. All right? Sound good? Okay. I want to continue with this example. We're going to do this probably a little quickly, but there's a couple things I want to tack onto this just to sort of get your brain scratching a little bit, going back to this whole strength of materials and structural analysis stuff. So let me go back to my little sketch pad, my little whiteboard. Okay, so we went through, let's recall a couple concepts. When we started to calculate all these section properties, one of the first things that we did is we referenced everything off of a datum. And that was important because when we got our centroid, we needed to know where it was. Everything was referenced from a common point. Okay? So here's our centroid, let's say, for this entire section. Now, there's a number of reasons why that centroid is important, okay, beyond just, calculating the moment of inertia. Let's bring it back to way back when. Let's sort of extend that page out a little bit. So I'm going to strike a line because I've got some stuff I want to talk about. Let's look at section moduli. Let me make this full screen so I can have a little more. All right, section moduli. Okay, so just so everybody remembers what we're talking about with this whole concept of section moduli, let's say I've got some beam, and it doesn't really matter. Okay, I got this beam, and it's subjected to, some load. It doesn't really matter. Something about like that, something about like that, something about like that. Whatever. It doesn't matter. Okay? And then I take this beam, and I cut a section. And I want to take a look and really investigate that section. So if I look at that section, it doesn't matter if I look to the left or to the right. I'm sort of zooming in. What do I got going on? Remember this? Remember I've got a bending stress profile that probably looks something about, I don't know, something about like that. Y'all remember that? That should be back from basic, mechanics, strength of materials, mechanics of foreign bodies, whatever the class was called, wherever you took it. This is just basic stress analysis. I have a beam, it is being bent. How do I characterize that stress? I characterize it with the formula sigma equals my over I. Y'all remember that, right? Okay. Where m is the applied moment at the section under consideration, wherever we're cutting the section, whatever the moment is there. I is our moment of inertia, which hopefully by now we've got a good refresher on that because we spent a fair amount of time last time looking at how to compute moments of inertia. Y is how far your point of interest is from the centroid, right? So remember, if you've got a beam, under bending, the centroid is where the bending stress is 0, right? Sound good? All right. So, a couple things. So our bending stress profile is linear. And we know that there's no bending stress at the centroid. All right? Where are our maximum bending stresses? Just based off of basic mechanics. It's either at the top or at the bottom. Now, if it's a symmetric beam, like if it's a rectangle or something, then it's the same, opposite in sign, but it's going to be the same value on the top than it is on the bottom. What we're dealing with in the world of bridge engineering, however, are beams that aren't the same on the top than they are on the bottom. They're very different, different size top flange than they are bottom flange. But we can come up with a quantity that'll make our lives a little easier by stating that sigma max is m over s. Okay, I can do a little bit better job than that. And I'm drawing that with hatches so you're not confusing that with a 5. Okay, So m over s, where s is a section modulus. Now, how do you calculate s? You would say that s equals I divided by c, where I is the moment of inertia. And c is what we call the extreme fiber distance. So when I say extreme fiber distance, what do I mean? I mean from the centroid to the way, way, way tippy top of the beam or way at the bottom. Make sense? Sound good? Okay. All right. Everybody okay with this? You need a second to write this down, or? Okay. All right. The reason why that's important is because I want to go back to this Excel sheet and I want to take a look at this. So let's look at this steel beam. Okay, so let's look at this calculation up here, the one with the gray heading up top. So this set of cells was trying to compute the moment of inertia of just the steel beam by itself. Okay. Now, what we saw from our calculations was this beam is not symmetric. I mean, first off, it's not symmetric by observation. You know, the top flange is 14 inches wide, the bottom flange is 16 inches wide. Okay. We've got different thicknesses and what have you. And the center of gravity is not very pretty either. I mean, it's 17.9, whatever, 99 inches. Okay. So it stands to reason that we're going to have two section moduli. A section moduli to the way tippy top of the beam, and then a section moduli to the way bottom of the beam. Sound good? All right. So over here on the side, I'm going to calculate two section properties. We'll sort of put this over here. Moses. I'm going to call this top of steel. Y'all still read that? Okay. And then I'm going to do top of steel, and I'm going to do one over here on the side. We'll call that bottom of steel. Okay. Now, let's go back. How do you calculate a section modulus? You take the moment of inertia, you divide it by the extreme fiber distance. So let's do the bottom one first. I think the bottom one's a little easier. So let's start off. Moment of inertia. It's in inches to the fourth, right? And what is that moment of inertia for this girder? It's this value right here, isn't it? That 15,968. That was the moment of inertia, right? Now, extreme fiber distance. Okay, so C. Okay. Now, what I'm asking you is this. Okay. C, we're looking at extreme fiber distance. And I'm saying that's from the centroid to the very, very, very bottom of the section. What is that value for this shape? It's the 17.99. Remember where we were measuring our distances from. We were measuring them from the very bottom. So that is our section modulus, or that is our extreme fiber distance right here. So we'll say equals that, right? So our section modulus, which is going to be in inches cubed, right? If I take inches to the fourth, I divide it by inches, that's going to give me inches cubed, is just that divided by that. So it comes out to be like 887 point something. And that's a really useful property if we're trying to determine bending stresses. Because if I've got a moment, and all I do is just divide by that, that'll tell me the maximum bending stress there on the bottom. That's pretty important when later on I might say, okay, let's calculate the bending stress on that bottom flange and let's see if that's an acceptable value. Maybe that stress needs to be less than the yield stress or what have you. So I might calculate it and see if it's less than 50 KSI or what have you. All right. Sound good? Okay. Now that's the bottom of steel. Let's do the top of steel. So same deal. Moment of inertia. Well, here, I'll just copy this. Moment of inertia. Okay, equals. That's obviously the same, right? Same moment of inertia. Now, extreme fiber distance. Okay, now this is where you got to pay attention. Okay, I'm talking about from the center, the centroid, to the way, 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 way tippy top. How am I going to calculate that? What? No. Okay. Total height minus y bar. I think you were saying 42. The what's that? Well, there you go. You got to count for all of it. See, what's the total height of the section? It's the thickness of the bottom flange, it's the web depth, and it's the thickness of the top flange. So we got to calculate the total height, then strike off that distance. That'll tell me that string fiber. All right, make sense? All right, so what do? We'll say that thickness plus that minus that. There we go. All right. Make sense? And just divide those two out. So what that means from a behavioral standpoint is looking at these section moduli, I can make some pretty straightforward assessments. Section moduli are in a way an assessment of the performance of a given section. So if I'm looking at these two section moduli, the section moduli for the bottom flange is larger. So that means in turn, when I apply moments, it's going to have smaller stresses than the top flange. See what I mean? That's kind of important. So you'd wonder, from a behavioral standpoint, you'd wonder, well, how can we get away then with such a smaller top flange if it's all made from the same material that arguably might have the same yield stresses? How can we make the top flange smaller? Well, there's a number of reasons why. One of the big ones is under vehicular traffic, it's not just that top flange in compression. It's the top flange and the deck. And that deck is carrying a lot of that load, so we can shave some weight off of that top flange. We can't shave too much of it, though, because that top flange has to be able to provide stability to the section under construction loads. Now, I'm getting sort of way into a hornet's nest of stuff that we're going to talk about throughout this semester, but it's just some points I wanted to make for later. In this world of bridge engineering, we really get the opportunity to tailor the size of this girder to the load demands. Okay, so these types of dimensions are very common. All right, sound good? Any questions? Okay. One thing I am going to do for what we do next, just to be consistent, I'm going to go back to my PowerPoint, and I'm going to go through, and I'm going to start to plug in these values for the negative bending region. So the flange sizes are all the same, or in terms of widths. The only difference is the top flange thickness gets a little thicker, and the bottom flange, or the web, gets a little thicker. This becomes 0.5. This becomes 1 1/8. So let's see. What do we got? So this becomes 1 1/8, and this becomes 0.5. Again, notice that everything else updated. Okay? Notice that everything else updated. Okay? This is just a point for later. I thought about this, and I thought this might be worth mentioning. You all probably are used to expressing things, this component of the beam is in compression, this component of the beam is in tension, and while that's going to be very important for later, right now what I'm really trying to do is express things as either the top of the section or the bottom of the section. The reason why I'm making that distinction is because in negative bending region it flips. Usually if I sit on this table, the top of the table is in compression, the bottom of it's in tension. Around the pier, that's backwards. Okay, the bottom is in compression. Okay, so to reduce confusion, I'm just going to say either the top of the beam or the bottom of the beam. That way we all know what we're talking about. All right, sound good? Okay. All right. So I went in and I replaced these dimensions with the dimensions for that negative bending region because I want to add in one more section, and I want to look at this steel plus longitudinal reinforcement. All right, so I'm just copying this down so that I don't have to reformat all this junk. I'm lazy. So, okay. So let's go back to this PowerPoint. Let's go back to this. Okay, so what I want to do is at least really briefly cover how I'm going to calculate this section with the steel plus longitudinal reinforcement. And it's not so bad, okay? we're going to have three shapes that we're going to need to consider. Remember, like over here with this non-composite beam, we had a top flange, a web, and a bottom flange. But then when we got to these two, we said, well, why treat it as four shapes? Why don't we just say the girder and the slab, right? Well, over here, we're going to have the girder, then the top layer, and the bottom layer, okay? And that'll be it. So let's start off with the simple one. Let's start off with the girder. Okay, so we've got three shapes. We're going to have the girder, we're going to have top layer, a little dark here under this screen, and the bottom layer. Okay, I'm going to delete this, delete that. Okay, so let's start off with the section properties for the girder. Do we need to go through and compute the area of the girder or this y distance for the girder or the moment of inertia? No, we went ahead and did that all up here, right? That's what that whole upper table was for. Because let's scroll up here. Remember, this upper table, that was the section properties for the girder, right? So the area of that girder equals this, right? The centroid of that girder equals that, right? The moment of inertia of that girder equals that. Now notice how these numbers look a little different than what I was dealing with before. It's because I changed all the dimensions. The flange sizes and the web sizes are different. Sound good? All right. So luckily everything else has already been sort of calculated for me. It's one of the nice things about Excel. You can kind of just copy and paste and everything's kind of nice. All right. Now we've got this top layer of reinforcement and the bottom layer of reinforcement. Now the nice thing about these computations is we got to determine three things: the area, the centroid, and the moment of inertia. I can do the moment of inertia really easily. I propose to you that the moment of inertia for these two segments is 0. Okay? The reason why is because what I'm doing in this section is I'm assuming I've got this, massive amount of rebar lumped into this really, really small space. And I'm asking, well, what's the moment of inertia of this one little value, this one little piece of rebar right here? And I'm going to assume 0. You go, well, how's it going to do anything? How's it going to affect the section? Because it's not just the moment of inertia. It's I plus AD squared. And that's where you get your stiffness. It's from the rebar, not from the moment of inertia, but from that AD squared. Okay. So we got the top layer and the bottom layer. So how do we calculate that? Let's go back to what the spec said. Okay, for the top layer, we say, all right, let's take the area of the deck. And what's the area of the deck? It's the effective flange width times that structural slab thickness, right? And then for all the rebar that goes in that deck, we say we take the entire area of that deck, we say 1% of it is rebar. And then on top of that, we say, okay, we got all this rebar. How much went on the top? We had some amount go on the top, some amount go on the bottom. Anybody remember? 2/3 went on the top, 1/3 went on the bottom. So put 2/3 on the top, and there you go. For the bottom, I'm going to do something similar. I'm just going to copy and paste the whole thing. But I'm going to say 1/3. Make sense? So I've got this big lump of rebar on the top, big lump of rebar on the bottom, 2/3 on top, 1/3 on the bottom. Sound good? And that's it. The only thing left to figure out are these centroids. I'm going to keep it pretty simple. All right? So let's deal with the top layer first. Okay. So keep in mind, let's sort of imagine this in our brains. We're going from the datum, which is the way bottom of that section, to where that rebar is, right? So let's imagine. We go up the thickness of the bottom flange, right? Then we go up that web depth, right? Then, if we go up the haunch, that puts us at the bottom of the deck, right? If we go up the structural thickness of the slab, that's the entire height of the section, right? Now, why would I do that? Well, where is that top layer of rebar? It's 2.5 inches down. How did I come up with that 2.5 inches? That's that cover requirement. Remember that? Remember, for de-icing salts in this area, cover requirement. Now, you could make the argument, well, wait a minute. Technically, the center of that bar should actually be a little bit lower because it's got a radius for close enough for government work. All right. So we're going to go Let me scroll up here a little bit. So we're going to go the thickness of the bottom flange, the web depth, the haunch, the structural slab thickness, minus 2.5. Make sense? And there we go. Now for the bottom layer, what are we going to do? Bottom flange thickness, right? Web depth, go up the haunch, and then what? Just go up 1 inch, right? And that'll put us there. So, oh, wrong place, right here. So equals bottom flange thickness plus the web plus the haunch plus 1 inch. And that's it. Luckily, the nice thing about Excel, it's already figured everything else out. So I don't have to go through and type all that other crap in. It's good. Any questions? That's it, really. That's all there is to it, really, to compute section properties. I've basically shown you everything that you need to do for your first homework assignment. Speaking of, let's bring that first homework assignment up so that you all know what's going on. Okay. All right. So here's your first homework assignment. Let me go ahead and pass it out. I think I got everything to work out on MU Online, so all you need to do, you don't even need to bring anything into class. Just whenever you make your Excel file, just submit it on MU Online and everything should be good. You just have to hit the upload button and everything's good. And that helps me out because otherwise I have to juggle a whole bunch of emails and I might have the tendency of losing it. So this sort of takes out the potential error on my end. Okay, that's 5, 6, 7. 1. I'll go ahead and give you all one in case you want it. There's that. 1, 2, 3. I'm getting the feeling I might have miscounted your. Oh, did everybody get one? Did you get one? Everybody got one. I must have printed one extra. Whoops. Oh well. Okay. I lose my Captain Planet points for the day. Okay, so what I want you all to do is prepare a spreadsheet that will compute the properties that we've discussed, fully. So I've even listed them out. So specifically, what I'm looking for are moments of inertia and section moduli for the following regions. So for the positive bending region, I need the non-composite properties. I need the short term for interior and exterior girders and the long term for interior and exterior girders. Now the negative bending region, I need all of that, but I also need the steel plus longitudinal reinforcement, again, for interior girders and exterior girders. The nice thing about Excel is a lot of this stuff is repetitive, so if you just keep track of your copying and pasting, you can probably do this assignment pretty quickly. So for your calculations, this first bullet point, that way so we're all on the same page, reference all your distances from the bottom like we did in class, that datum from the bottom of the section. Let's see, for clarity, put all your positive bending regions, calcs on one sheet and your negative bendings on another. A hint, I would work on your negative bending region first because the difference between the negative bending region and the positive bending region is they're the same, only the positive has less. So if you do the negative bending region, just copy the whole sheet over and delete a couple rows and you've got the positive. So one big thing is the calculation should be somewhat neat. I mean, I've been doing it pretty rough here on the board. I'm going to show you something real quick. This is a sort of a template I made up. I mean, this isn't anything, massive or anything massively special. This is just something I sort of came up with. But I've got sort of the heading that you would see on a typical set of engineering calcs. You can see we're looking at the positive bending region. I've got all the section dimensions in, and then I've went through and organized this out. So you can see I've got non-composite section properties, short-term interior, short-term exterior, and you can see where they would be filled in. I went through and I put top of steel and bottom of steel for all the section properties. If you want, you can do top of concrete for all of these ones that are in the composite sections. I'm not terribly worried about that right now, but I would like to see top of steel and bottom of steel for each one of these sections. And and there we go. Now negative bending region, it's the same story, only there's more going on because I've got the steel plus longitudinal reinforcement going on. And I put top of reinforcements here, but I'm not really worried about that. Really what I want to see is top of steel and bottom of steel. All right, sound good? Now, one of the things is, look, you all are going to be using this quite a bit, so I want you to build it the way that you would use it, okay? So be familiar with it and be comfortable with it, you know? Make sure it's well organized because you're going to be referring to this stuff quite a bit. I mean, simple things like when we do live load distribution factors, you're going to have to compute kg. To compute kg, you need a moment of inertia. You need to know where to find it, okay? So you need to be the one in charge of building this, not for my sake, but really for yours, okay? Sound good? All right, so this is due next Tuesday. Again, you really shouldn't need to bring anything to class. Just upload it before. I think I put 6:30 p.m., so that's, you know, when we're in here. So sound good? All right. I do want to go ahead and jump into this next lecture, and then I guess we'll take a short break. If you've had me for a structural design course before, chances are you've seen this in some fashion or another. But I want to at least frame the discussion for those of you that haven't had me for a structural design course before, because there's some stuff in here that I think is really important that if you don't know where this stuff comes from, I think it's worth discussing. Those of you who've had like pre-stressed concrete or something like that, have y'all heard about that whole 1.2 times the dead plus 1.6 times the live? Is that familiar? You heard that before? And if you've had steel design or concrete design, I know you've seen it before. Okay? Everybody's heard that before. Right? If it's been a while, no big deal. What I want to do is talk about where that stuff comes from. In other words, what is our design philosophy that we use? You're going to hear me use the words or the acronym LRFD quite a bit. And LRFD stands for Load and Resistance Factor Design. I want to talk about what that means and why we use it. And I'm going to get a little mathematical on you, talk a little bit about statistics and things like that, but I'm not going to get crazy into it. I mean, we could do a reliability lecture and get nuts with the statistics. I can see you all are just jumping with excitement at the mention of statistics, right? No jokes. I mean, come on. Again, I'm going to be full of a lot of cheesy, corny jokes throughout the semester. You're just going to have to get used to it. All right. So let's go back to basics. Let's make sure that we understand why the heck we're all in here, okay? Let's talk about structural design. What is the goal of structural design, okay? I've got some situation, you know, a beam, a column, what have you. That column is subjected to some, or that beam is subjected to some loads. Dead loads, live loads, snow loads, wind, whatever, okay? My goal as a structural engineer is to figure out how big that beam needs to be, you know, size, its flanges, its webs, what have you. It's my job to size that beam so that it safely resists those loads. That's it, right? That's my job as a structural engineer. Now, how do I do that? Now, there are a number of philosophies available to us as structural engineers. Some of these, you know, even if you don't have much experience in structural engineering, some of these philosophies you've heard before. Things like allowable stress design, allowable strength design. You may not have heard it called that, but I'm sure you've used it before. What we're going to use is LRFD. Now, what do I mean? Let's start off with allowable stress. Okay, so allowable stress is a pretty basic concept. Okay, I go down to the lab and I take this table with me down to the lab and I take it and I put it under an actuator because I like breaking things. My general philosophy is any day with controlled demolition is a good day. So I put it under an actuator and I start pressing down on this thing until, boom, it breaks, okay? And let's say I do the math and I find that this table breaks at 800 pounds, okay? So I know that this table will physically fail at a load of 800 pounds. Now, I'm a table salesman, and I'm going to sell this to a number of consumers who are going to put this in classrooms and offices all over the world. Do I want to tell these consumers that this table can withstand 800 pounds? Probably not. Probably what I would do is say, you know what, let's put on the package that this table has a maximum capacity of 400 pounds, okay? So that way, there's a little bit of a factor of safety built into it, okay? So that's what I mean by just fundamental design philosophy. That's about the most basic design philosophy that we could use. You know, we can go and test materials, test components, and determine what I would call their nominal capacity, or in other words, their real actual capacity. What's going to happen when we violate that? The section is literally going to fail. And then we say, let's back that off a little bit. And we use that factor of safety based on, trying to capture the uncertainty with a little bit of engineering judgment. And don't get me wrong, we still use this for a number of different scenarios even to this day. It's pretty tough to come up with a calibrated design philosophy for something like geotech. Anybody who's got any experience in geotech will tell you that go drill right here and go drill over there. You're going to get different soil properties. It's going to happen, okay? So you're going to have to just, I don't want to say wing it, but at some point you've got to just go with a factor of safety that makes sense, okay? And there's judgment that goes into that. Now, fortunately for us, we're dealing in a world in structural engineering where we can classify those uncertainties pretty well. For instance, let's go back to my table analogy, all right? So I go down to the lab and I break this table, and it breaks at 700 pounds, right? Are you telling me that, let's say I'm in a really destructive mood and I want to break every table in this room. Are you telling me that this table is going to fail at exactly 800 pounds as well? Come on, no, of course not. You can't tell me with certainty that these tables are made and manufactured exactly the same way, that they have the exact same material qualities, that there's no flaws. You're telling me that each one of these bolts and screws are drilled to the, tenth of a millimeter accuracy. No, there's going to be differences, okay? So if I went and tested and failed every single table in this room, there'd be some scatter, right? There'd be some statistical uncertainty with that data that we could address, right? Things like material quality, fabrication tolerances, how they were constructed, etc. Same thing with the loads. You tell me that if I go to a design code and it tells me what the base wind speed is, that is exactly the base wind speed that I will always see on that building all day, every day. No, there's going to be some variability with the loads that we see. There's uncertainty with load estimation, possible overloading. In the world of hydrology, we like to use things like the 100-year storm or the 50-year storm. Go to Clay County. They know about storms that go past that. I've done some volunteer work there recently, and they recently saw 1,000-year storms. It was pretty damaging. So there's all sorts of uncertainty associated with this. Let's start to look at this in that fashion. All right? That's where LRFD comes into play. We start to look at it in an uncertain fashion. And when you're dealing with uncertainty in the world of math, that gets into probability, okay? Trying to account for those uncertainties in the world of design and in the world of engineering selection is what we call reliability. So if you ever hear the term reliability, that's what we're talking about. Now, let's keep it basic. Because if you get into advanced statistics, there's all sorts of different probability distributions and all that stuff. I'm not getting into a hardcore statistics lesson today. I just want to frame things in a term we can all understand. So going back to the tables, if I break every table in this room, there's going to be some scatter to that data. And that scatter may be represented by something like a normal distribution, right? Might have a mean, a standard deviation. You all have seen plots like this before, right? Hopefully. I'd hope you've gotten to a master's engineering program with at least seeing a bell curve before. All right? So what I'm doing is I'm going to look at things from two sides of the equation. I'm going to say that there's an uncertainty associated with the resistance, how strong the structure is, and there's an uncertainty with the loads, how much force I'm putting on the system. Now there's a couple things to note. First off, notice how the resistance curve is over here. It's to the right of the loads. Everybody see that? The R curve's over here, the Q curve's over there. That's a good thing because on average, we want the structures that we design to be stronger than the loads that they're subjected to, right? So if that was the other way around, we as structural engineers must not have known what we were doing for the last 5,000 years of recorded history, right? So ultimately, we want that to be over here. Now, a more subtle point is that you notice that the resistance curve is a little skinnier and a little taller, right? Notice that? Okay. Now, if you go back to problem stats, what that means is that the resistance curve has a smaller standard deviation, which should be the case. I mean, as an engineer, I have a whole lot more control over what this table looks like when I'm done with the design than I do with John Doe, who's purchased this table. I don't know what they're going to do with it. I, as the engineer, should have more control over the resistance of the structures I design than the loads they're going to be subjected to. Make sense? Everybody good? Okay. So what I'm then going to do is say, well, I've got these resistance curves. I've got these load curves. Let's do a new one. Let's do what I'll call a Z curve. And you can call it Z, you can call it A, B, whatever. There's nothing special to it. What I'm going to call this curve is a system function curve. Basically, I'm going to say it's the resistance minus the load. So I'm just taking the resistance minus the loads and plotting that. Okay? Now, this one gives us a nice little measure of the safety of the system, because think about what happens. Just look at this mathematical expression. Let's keep it simple. Anything on this side of the axis is any value where Z is greater than 0, right? Anything over here is anything where Z is less than 0. Basic, right? Sound good? Well, if Z, let's look on the right. If Z is greater than 0, how does Z become greater than 0? It becomes greater than 0 if this number is bigger than that one. If this number is bigger than that one, that means the resistance is larger than the loads. And if the resistance is larger than the loads, that's a structure that's not falling down, right? Make sense? Over on the right, the other way around. Now the loads are bigger than the resistance. If the load's bigger than the resistance, what's that mean? Bridge is in the river, right? So what we want to do really is control this shaded region. That's what we call the probability of failure. That's all the regions where the structure is deemed unsafe. See, there is no such thing as a perfectly safe structure, or likewise a perfectly dangerous structure. I guess the only perfectly dangerous structure is one that doesn't exist, right? There's no such thing as a perfectly safe structure, but what we can do is limit that probability of failure to an accepted level that we in the structural engineering community deem acceptable. You take steel design, you take concrete design, take pre-stressed, where you focus in the building side, and you've probably seen things like 1.2 times the dead or 1.6 times the live. You've probably seen that before, am I correct? Okay. If you've seen that before, what that is when we use 1.2 times the dead and 1.6 times the live, those numbers come from trying to keep this probability of failure uniform. I mean, why is the live load number larger? Why do we use 1.6 for the live loads and 1.2 for the dead loads? Well, live loads, there's a lot more uncertainty. You know, if I take this building, I, as a structural engineer, should be able to estimate, you know, like if I'm looking at a floor system, how much these ceiling tiles weigh, how much the wiring weighs, how much the lights weigh, how much the HVAC and the microphones weigh, how much the concrete slab weighs, how much the floor beams weigh. I'm not saying I'm going to get it perfect, but I bet you I have a better chance of estimating how heavy that floor system is than I do estimating how much load's on it right now. See what I mean? There's more scatter associated with the live loads than there are the dead loads. That's why with the live loads we use 1.6, and with the dead loads we use 1.2. Make sense? Okay. All right. Now, what we do in the world of reliability is we measure that uniform level of safety through what's called a reliability index. Basically, how many standard deviations we are away from the y-axis. And the reliability index changes depending on what we're looking at. If we're doing main member design, a reliability index of around 3.5 is usually pretty acceptable. But for connections, we tend to use like 4.5. Because, look, don't get me wrong, if a main member fails, that sucks. But if a connection fails, you got multiple members framing into that connection, that's worse. Make sense? So that's why we're a little more stringent on connections. Like if you remember, if you took steel design and you look at, let's say, tension members, the resistance value, that phi value, it's 0.9 for yielding, but it's 0.75 for fracture, because you're looking at that connection region. It's more stringent there. That's why we use that lower resistance factor. So just bringing it back. All right. Now, this is just the formula for if you wanted to compute that, if they were two normal distributions. If you're dealing with normal and log normal or different loads, this stuff can get really hairy really quick. That's where reliability comes into play. We could spend all semester on that. So I will leave that to statistics professors for another day. All right. This is a measure of something that I think is really important. So this was a study looking at what those reliability indices. Remember, those reliability indices were how far from the norm or how far from that y-axis each structure was. Now, this is actually from the bridge spec. This is before the adoption of LRFD. So if I look at bridges that are on average 30 foot in length, the reliability index is all over the place. It's anywhere from like 1.5 to 3.5. It's not controlled. It's scattered. It's all over the place. After we started using LRFD, we got a much tighter control on that reliability index. Okay? So I'm not saying LRFD is perfect, but we get much more uniform and predictable levels of safety than we do with something like ASD. Okay? This is unavoidable in something like geotech. But in structures where we're dealing with manufactured products like bolts and plate girders and things like that, we should have more control over our design than we can in something like, I keep going to geotech because it's one of the most unpredictable worlds of civil engineering that there is. I mean, you go to the world of geotech, you find a lot of what I might consider over-design. A lot of it's just good engineering judgment because it's so uncertain. So it is what it is. All right. So just so everybody's clear on what I mean by LRFD, when we use LRFD, we're not just applying a rote factor of safety to the whole thing. We're factoring both the loads and the resistances. So when we look at resistances, we have this nominal resistance, in other words, the go down to the lab, press on the table, it breaks resistance. We then adjust that by a phi value to obtain a factored resistance. That's the one we can use for design. Likewise, on the loads, we calculate these nominal loads, or in other words, our best estimate as to what those structures are actually seeing. Then we bump them up a little bit. We bump them up a little bit to account for that uncertainty. All right? Ultimately, what we'll get is an expression that looks like this, that your design resistances have to be greater than or equal to your design loads. Now, if you've had me for an undergraduate course before, this ADA term is probably new. We'll talk about that today. But what I'm going to do, I think, for now is take a little bit of a break. What are we at? We're at like 7:30 or something like that? What's that? 7:25. Tell you what, let's take a few minutes. We'll take like a 5 or 10 minute break. 7:25, want to get together around 7:35, 7:40, something like that. We'll get back into it. We'll start digging into the spec, and then we'll start attacking one end of the equation, which is loads. So, all right. I could sure use, my throat could sure use a break.